All right. So hopefully you can hear me well. So first of all, thank you very much to the organizers, John, Lenka, and everyone else for inviting me. First of all, to put together such a wonderful conference. I certainly learned a lot, and also to invite me to come and share some of my recent research with my collaborators and maybe some thoughts on the progress in machine learning and its interactions with scientific computing, dynamical systems, and so on. To provide a bit of background on what I'm going to talk about today, we all know that machine learning has been making tremendous amount of practical progress in a variety of fields. It started with machine vision, and goes into natural language processing, and finally gameplay. There's a lot of high-profile success in that area. However, as is mentioned in several talks in this conference, the theoretical part of machine learning is somewhat lagging behind. However, of course, there's a lot of progress, which is very nice to see. But at the core, there's still a lot of mysteries waiting to be uncovered. And why this mystery is very interesting and also highly relevant to this interplay of machine learning and scientific engineering is that science and engineering is that we're recently seeing a lot of new applications of machine learning outside of these fields, but more in computational science and even experimental science. We're seeing a lot of new techniques being developed and new problems being posed. So with all these emerging applications, it is really both important to understand the theoretical underpinnings of deep learning or machine learning in general, and also to see whether these new angles of attack will provide us with new solutions to some old problems. So before we can sort of discuss what is the mystery, we have to really think about what is new when it comes to these modern machine learning techniques that we are being introduced to. So I will argue that one of the, definitely not the only one, but one very interesting structure that we observe in a lot of new machine learning models and data and algorithm is compositional or dynamical structure. So on the model side, it manifests itself in the very architecture of this new machine learning models we're using, in all kinds of applications. For example, in deep neural networks, the distinguishing feature of a deep neural net is pretty much the word deep, right? So it consists of a lot of shallow layers being composed together, and together they form a very powerful function approximation or inference machine, right? And then, of course, the recurrent neural network used very widely for time series modeling has even a more, kind of a compositional structure than the deep neural networks, in the sense that the recurrent connection goes on theoretically forever, right? So this is a very, very deep network. But besides model, we look at some new applications of machine learning in the data in the scientific discipline. We also see that a lot of data has this dynamical structures in it as well. For example, we want to try to apply machine learning to predict the trajectory of certain molecule in configuration space. There, you're dealing with a time series. In itself has some dynamical structure. Often you can actually ascribe some description to these structures, and how they interact with the model is extremely interesting. And finally, on the algorithm side, we have a lot of new developments. For example, in optimization, for example, in the stochastic setting, the stochastic gradient algorithm is widely used to train neural networks. There in itself, the algorithm also has very interesting dynamical properties. In this time, the things evolving in time are these weights of a neural net, for example, under training. So you can see that these compositional and dynamical structures are present in a lot of areas of modern machine learning. And why do I use these two words, interchangeably? Perhaps is good to spell out is that if you think about composition and dynamics, essentially they're the same thing. Because if you look at a compositional function on the left-hand side, right, I'm composing this function many times. We can also think about this as a dynamical system, where for example, the input to this function, this compositional function, can be thought of as the initial condition to a certain dynamical system, and the output can be thought of as the final condition or the final state. And the repeated composition can be written in the form of this discrete iterative equation, of which the time you can identify it as the layer or the compositional structure, the index of the composition. So really, this connection underlies the study of dynamical systems. Is precisely, thinking about how we can visualize or study or understand this kind of repeated composition or repeated dynamics, some interesting behavior that arises out of this structure. So this is the topic of dynamical system, and this is how I think we can understand the connection between modern machine learning and dynamical system. So if you want to think about the connections, I like to think about it in terms of three rough categories. Now, the first category is called machine learning via dynamical systems. So this is where we try to use machine learning tools, dynamical systems tools, for example, differential equations, optimal control, numerical analysis, to try to understand and improve upon this machine learning architectures, models, algorithms that we otherwise discovered without seeing this connection, right? So so this is one area where the dynamical systems theory can try to contribute towards the theory of machine learning, deep learning, for example. In the second category, which we can call machine learning for dynamical systems, this is where we can try to analyze or develop tools that uses data-driven means, use machine learning, for example, to accomplish some task involving dynamics time. For example, time series forecasting. When we try to use machine learning to do time series forecasting, you are dealing with the data, or data generation process is inherently dynamic, right? So you're trying to use machine learning to predict certain behaviors of a dynamical system. Now, this is interesting because it gives you a nice interplay between the machine learning architecture, which in itself has some dynamical structure, and the data and the data generation process, which is also a dynamical system. We'll see an example of that later on. And finally, in the last category, I call it machine learning of dynamical systems. So this is where the goal is to do a data-driven discovery of a certain dynamical system from the observation of its trajectories. Okay, so this, in some sense, is one of the most basic problems of data-driven, scientific data-driven inference methods, right? So, for example, one problem statement will be: how do you learn a representation of a dynamical model, let's say a differential equation, from observing its trajectories? Or more often than not, you want to construct a model that's perhaps lower dimensional than what is being observed, because usually, in experiments or in simulations, we are usually dealing with very high dimensional dynamical systems that are difficult to analyze. Okay, so one problem statement is also to reduce that dimension and come up with a lower dimensional model that also captures the key properties of the system. Okay, so of course, these are not going to be distinct categories, and there's a lot of interplay between these categories as well, but I think it's useful to think about interaction in roughly these three ways. Now, with this different categories of connections, the natural question to ask is what kind of mathematical or practical questions are we really interested in, okay, in each of these categories? And I think it's useful to use supervised learning as an example to illustrate some of these possible questions. So in a nutshell, supervised learning is about learning how to make predictions, right? You have a data set which consists of inputs, okay, which I call it X, and some outputs, which I call it Y. And there's some underlying relationship between them, modeled by some function that maps each input X to output Y. Okay, so for example, in image recognition, you have cats and dogs pictures being mapped into the label cats and dog, vectorized in some form. But of course, in a dynamical setting, you could have X being a time series, right, up to a certain time. This is a stock price up to today. And your goal and F star, this target function actually maps each of this time series to one with a longer time horizon. So this will be, in the sense, a predictive problem for time series forecasting, for example. And the goal of supervised learning in both of these cases is to learn approximate this target function, or more generally functional, F star, okay? And how do we do that? Is from using information from a data set of observations. Okay, so the process of building such a model has two essential steps. The first step, we define the so-called hypothesis space, H, which basically consists of a set of functions that we we can deal with more easily. All right, so for example, we assume or we hope that this relationship, unknown target relationship F star, is closely modeled by some H that we can easily write down. Like for example, in the simplest case of linear models, this H is just a linear combination of basis functions. Okay. But of course, we can think about more complicated cases for shallow neural networks. This will be very similar to this basis functions, except that this basis functions, which is in the form of the usual fully connected neural net, its parameters are not fixed a priori, so they can be adapted to the particular task. So you can think of this as a adaptive basis or a nonlinear approximation kind of framework. And then, of course, deep neural network is interesting in that it builds its complexity by composing these many functions together, where each of this f is a shallow neural net. Okay, so the first step is to define some sort of hypothesis space. Now, once you have defined a hypothesis space, the second part is to find one particular best, okay, in quotes, function f from this hypothesis space so that it makes very similar predictions, as similar as possible, to some target f star. And how do we do that is usually through empirical risk minimization. Okay, so what is this? This is basically we come up with a loss function phi, which measures the distance between the prediction of my model, okay, that's in my hypothesis space, and the prediction of the ground truth, right, which is f star, the target, which is y. And we penalize the difference between them, and then we average this over a sample set of size n, and we minimize that. So we find the best possible hypothesis or the function of hypothesis space such that it agrees with my target on these samples. Now, this is empirical risk minimization is what we can solve because we have these samples. However, what we're really interested in solving is the so-called population risk minimization or the expected risk minimization. Okay, so this is where we want to minimize not just the loss function over all of my training samples, but really you want your model to be able to predict on a sample that they've never seen before, right? Hopefully, from the same distribution, but it's not seen before. And that's where the model is set to be able to generalize. So here, what we really want to minimize is this risk, which replaces this sample mean by expectation over mu star, where mu star is the input-output distribution. Okay, so this is a joint distribution of the input and output. Now, what we can solve is the first one, but what we want to solve is the second one. So of course, there's a gap between them. Of course, this gap also depends on the number of samples you have. Okay, so with this two-step setup, we can then try to organize what kind of questions we can ask. And there's three kind of paradigms of questions we can consider. The first one, in some sense, is also the most basic, is the problem approximation. So it basically asks if we have a hypothesis space H, and some target function or functional here, what is the closest you can get to this function, right? And the distance we call it approximation error. So here is the best model. Okay, so our hope is that this hypothesis space is complex enough such that this approximation error for a large set of targets is going to be small. But of course, this is not the only problem that one can consider. Because even if I tell you that it's a very, very good model, this best model is really close to the target, you're not sure how to find it, right? So, and in fact, most of these improvements is really at how can you possibly find such a model, well, okay? And this is what we can call optimization and training or learning, all right? So we start with some initial guess, and we use, good algorithms and also good data to try to get close to this best model. So we get some learned model that's hopefully closer to the best model than the initial guess. But however, these two are not the same. Okay, so there's still a gap in between. And the first reason that there's a gap in between is because we usually use some sort of iterative optimization algorithm. At any finite number of iterations, we're going to have some errors, right? And this error is in fact optimization error. And this is the distance between a learned model and your empirical risk minimizer, which is the optimization problem you're trying to solve in order to learn. And finally, there's still a gap between the empirical risk minimizer and the best model, which is the population risk minimizer, because your sample is finite. Okay, and this distance is usually called the generalization error. So you can see from the learned model to the target, there's really three errors at play. And they're all relevant in characterizing, how far your learned model is from the best possible from the target. Okay, and I think one interesting remark is that each of these errors has been the focus of studies in different fields, well, related but slightly different fields. For example, approximation error is studied a lot in approximation theory, harmonic analysis, And generalization error is the principal object of study for statistics, right? You try to give you a finite number of samples and you try to estimate what is the difference between your learned parameters, or trained parameters, and the ground truth. And finally, optimization error is, of course, the study of various optimization algorithm convergence bounds. And machine learning, supervised learning setting gives you a nice opportunity to try to combine them and see how they interact with each other. So the goal, when we look at this dynamical view of new issues that arises in machine learning, is how does approximation, optimization, generalization aspects of machine learning, how does it interact with dynamics? Okay, and that is one of the main goals of what I'm going to discuss today. So the first one I want to talk about is the first category interactions, which is machine learning via dynamical system, where you try to use machine learning, try to use dynamical systems tools to try to understand various aspects of machine learning. And one basic question, concerning deep learning is, as we said before, deep learning has a dynamical structure, right? So why is deep learning different from, let's say, a shallow neural net? Now, one reason, which is its namesake, is that it's deep. So shallow neural networks, as we understand, behaves very much like, a lot of these basis models. Okay, so in the sense that it builds complexity by increasing the number of nodes, which is essentially increasing the number of linear combinations that you process, okay, to build a target, to build an approximation of a target function. Okay, so although this basis is adaptive, at the end, this increasing complexity in the width direction just gives you more basis function. However, for the deep neural network case, at least the new phenomena that arises is increasing complexity in the horizontal direction, which is stacking more layers together to increase complexity. Okay, so this is the new phenomena, and the goal is really to understand, for example, from the approximation side, how do you achieve approximation or universal approximation of any function via composition, which is essentially dynamics, right? Instead of increasing the number of linear combinations. And then the second question on the optimization side is, how does this learning process interact with this dynamical structure that's present in a neural network? Can we say something about this that behaves differently from this? Okay, so focusing on difference is going to be our goal. So the primary tool we're going to use here is a continuous time idealization. Okay, so instead of considering a discrete kind of neural network with discrete layers, it is often useful from an analytical point of view to think of it as some continuous dynamical system in some limit. Now, this approach, in some sense, is a modeling approach, and is definitely not new to us, right? For example, in a lot of studies of physical chemical systems, we do exactly that, right? For solid and fluids, if you zoom down to the molecular atomic level, they are discrete objects. But it's often useful to sort of zoom out and think of them as continuum objects, okay? And that gives us these very nice PDEs that we can predict a lot of these macroscopic properties. And the same thing we want to do, we want to do the same thing for this neural networks, right? So taking a deep residual neural network, so here each layer is in the form of a difference equation, where the next layer's features or the hidden states depends on the previous one via addition of the previous state plus some nonlinear transformation. So this Fk is just a general representation of the kth layer's nonlinear transformation. And we can then idealize that as really a continuous time dynamical system where this t is now a continuous variable that plays, in some sense, the infinite limit of this number of layers. Okay, and doing so allows us to introduce to connect it with very classical areas of mathematics that will help us do a lot of this analysis. And most importantly, the dynamical aspect of both of this discrete and continuous time remains the same. And this approach has been introduced in 2017, 16 and 17, and of course in the machine learning community has been made popular also via the work of neural ODEs. Okay. So from the approximation point of view, what we want to, of course, ask is how can we approximate functions using a propagation of dynamics, right? So how can dynamics actually help you achieve approximation of a certain function? Now, to visualize this, I can show you in some sense a very toy example. Now you have a two-class classification problem. You have these dots, different color belongs to different class. And this is not linear separable because we cannot draw any straight line to separate these two classes. But what we can do is to evolve this under some dynamics. So we use each of these points as an initial condition of a common dynamical system. Okay, we construct some sort of time-dependent dynamical system, and then we evolve it. And let's see what happens. Okay, so under this temporal evolution, you can see that this two sets of points starts to unravel. And at the end of my evolution, separating these two classes of points becomes extremely easy. Okay, so this is a toy example, but it tells us, it's instructive in the sense that dynamics can help us rearrange or transform the domain of a very complicated function into one that is much simpler. And then we can use a very simple function at the very end to achieve approximation. Okay, so if we write that in a more precise language, we can think of the compositional approximation once you take this continuous time viewpoint, of course, as a following problem. So we have some input x, which is mapped onto some output y. Okay, this is and this basically defines a function f star. Okay, this target. Now the dynamical or the compositional approximation method goes like this. We take this x and we put it into the initial condition of a dynamical system. Okay, this is a continuous idealization of a very deep neural net. And then we evolved it through the dynamical system. And this ft is the right-hand side of the dynamical system, the vector field. But you can also think of it as the layer, right? Each layer's nonlinear transformation, which you can adjust every layer. So this ft belongs to some set. Okay, and you arrive at some terminal state xt, and hopefully here you basically unravel the domain so that now it becomes a very simple function to approximate, and we can just apply a very simple function g to approximate this and give us a y hat that's close to the predictions of my original target function. So here, there's really two parts of this transformational. There's two parts of this hypothesis space. The first part is a family of transformations induced by this dynamics or this flow. Okay, which is essentially the flow map of all possible dynamical systems you can consider, where ft, each layer or each vector field belongs to some general set of functions. We call it f, curly f. Okay, and of course, this depends on the terminal horizon as well, so it's t. And then finally, we have this terminal family, which is usually a very simple family of functions. You can think of it as a last layer of a neural net, usually a linear layer. And then our dynamical hypothesis space is simply the combination of these two, right? So we basically compose G with phi, and then we take the union over all possible times. And this gives us the hypothesis space of mappings that's used to approximate f star. And you can see that this hypothesis space only depends on two things, which is f, how complex is each of my layer, and g, which is the last layer, which is usually very simple. Now, the key question here would then be, in this abstract setting, can we achieve universal approximation by using a very simple f and a very simple g? Okay, so by doing so, we know that all the complexity is built through the composition or through depth or through dynamics. So it turns out you can actually prove a general sufficient condition for that. So essentially, we can show in this work that in dimensions greater than or equal to 2, we can always achieve an approximation by this dynamical, dynamical structure, which is the idealization of deep residual net, provided you satisfy some conditions for G and F. Okay, so 1 and 2 conditions are essentially some very weak conditions that are usually satisfied by any reasonable choice. And the third one is probably the most interesting. So I'll talk about that. So the third one says that the right-hand side of your vector field, which is your neural net, if you take the convex hull of all possible configurations of your nonlinear function, it has to contain a function which we call a well function. So what does a well function look like? It looks like a well, right? So at the bottom, it is flat, it's 0, and it's 0 in some set omega, which is a nice set, like a convex set. And then outside of it is all non-zero. Okay, it doesn't have to point upwards. It can point in any direction. And of course, you can generalize that notion to multiple dimensions. So once your convex hull of your each layer, right, actually contains such a function, then you can use that to show that you can achieve universal approximation by just composing them. And in some sense, the understanding is that this kind of functions induce some rearrangement dynamics, because if your points lies in the middle of the well, you can not move them, right? And if it's outside of the well, you can move them using this well. So that is basically the intuition, and you can prove that this is actually sufficient. So what's interesting about this is that it doesn't really say anything about the architecture of your neural net, right? I didn't assume that neural net is of a Relu form or some other activations or some other form, but rather, if you abstract this problem into a dynamical systems approximation problem, there's only some very weak conditions your dynamical system has to verify, and you can check that a lot of this neural network architecture actually verifies this condition. Now, what's interesting is in dimension one, this is no longer true because of some topological constraints. But you can show that if you have additional assumptions on your target function, for example, if your target function is increasing, then this is still true. And in dimension one, we can also prove some rate estimates, which I will not talk about too much. And there's some very interesting connections between this kind of results with the classical study of controllability. So controllability basically says that if you have a dynamical system that can steer a finite number of points, can you always arrange these points to a position that you want? Okay, and a lot of this analysis depends on some Li theory that requires a lot of smoothness conditions, but they are related. Okay, but the approach here is a bit different. Okay, so here this is a basic some basic results on approximation problems. But of course, this is not the entire story, right? Because even we know that dynamical systems under very weak conditions can approximate arbitrary functions through its flow map, it doesn't tell us how to find it, right? So how do we actually understand the optimization problem? Or rather, if you think about the empirical risk optimization in this dynamical setting, is there any new phenomena that arises? So it is more instructive then to think about how do you formulate this empirical risk minimization by taking into account this dynamical structure. So if we write this learning and optimization problem with this dynamical hypothesis space, you really see something like of this form, right? So essentially, okay, this is population risk minimization. So we are minimizing over the input-output distributions. Here, this loss function is the usual loss function, like mean square loss or cost entropy loss, that's defined on your label and of course on the output of your network, right? And this is only determined, since it only depends on output, it is at the very last layer. And then you have some possible regularizers that depends on all of the layers. So we can think of it as an integral of some function, loss function. And T now is the continuous analog of a layer. And then, of course, this layer, each layer, the features are not independent. They are connected by some differential equation, okay, in which theta t is just the neural network weights at the tth layer. Okay, so if you look at this problem, once you bake this dynamical structure into it, it looks very much like a control problem. So what is a control problem is where you have a differential equation with some parameters you can choose at every time. And your goal, you can think of this as some steering parameters or control parameters. And your goal is to steer the system so that you minimize some loss that depends on the end state and also depends on some running cost. So each time you incur some cost. So the general empirical risk, population risk minimization is very much a control problem once you build this dynamics into consideration. And in fact, this is slightly different from the usual kind of control problems we encounter in control theory and dynamical systems, in the sense that it is a mean field problem. We are not just controlling one point or a finite number of points. This initial condition of my dynamics and the terminal loss, which depends on your label, right, y, are themselves random variables. They are drawn from some distribution, okay, mu star. And you have to apply the same control, theta t, okay, to this entire population of possible initial and terminal states. So this is why we call it the mean field control problem. And then this raises some theoretical and practical questions. The theoretical question is, in this mean field setting, what are some necessary and or sufficient conditions for optimality? And based on that understanding, is there some ways to understand or improve upon this learning algorithms that we use for deep neural nets? Okay, so it turns out that we can actually say something about the necessary and sufficient conditions. And we know that in classical control theory, which is some major results are obtained by Pontryagin and Bellman, they are in fact the result, an analog of both of these results. Okay, in the necessary condition case, we can actually prove that there is a mean field Pontryagin maximum principle that is satisfied necessarily for extrema or optima of this deep learning based control problem. And finally, we can also prove a necessary and sufficient condition through Hamilton-Jacobi-Bellman equations, which is the again a mean field analog of Bellman's condition for optimal control and dynamic programming. And from this understanding, we can actually design some algorithms based on, for example, the Pontryagin maximum principle that in some sense generalizes the backpropagation algorithm. Okay, so you can think of backpropagation algorithm as a special case of implementing some maximum principle, basically solving for the set of conditions that satisfies the Pontryagin maximum principle. And from there, you can extend it beyond backpropagation to deal with cases where you cannot straightforwardly do backpropagation. For example, for networks that are quantized. So in this two works, we explore the algorithmic consequences of this approach. And more recently, we can also look at this control approach and ask, what else can it do other than train a network? Okay, and a very popular thing that the control systems can do is try to stabilize the system, right? So if you have some perturbations of your system away from some intended trajectory, then, for example, like a motion of a rocket, very important role a control system plays is to counteract that perturbation. Now, this perturbation is actually a big problem in deep neural networks because when you have a slight, malicious perturbation, if you will, on the input, it is found that you can actually change the output. Okay, so the input is very small perturbation can result in a very large perturbation of the output. And we can then ask, since control systems, in particular closed loop control, can help alleviate that problem in traditional dynamical systems, can we also apply the same thing? And it turns out that we can, and we can yield some robustness algorithms that can achieve good performance for to counter these adversarial attacks. So these are some of the applications of this optimization approach where you treat this optimization problem as a control problem. And finally, on the machine learning via dynamical system side, I want to talk slightly about, we talk about model and optimization, but the optimization algorithm itself also has some interesting dynamical structures. So for example, in the empirical risk minimization, very often what we do is to write down the empirical risk, which is the over a data set. Okay, and this is a loss function. And what we do is to train it using some gradient descent algorithm, for example, stochastic gradient descent. Right, and this and with some learning rate eta. So here is stochastic in the sense that instead of taking this full data set, I'm going to take dk, which is random subset of d. Now, what's interesting is that this dynamics can be very complicated. Okay, so for like a loss landscape that you encounter in deep learning or other applications, this landscape can be very complicated, and it results in very complex dynamics of this data. Okay, and understanding this training dynamics is very important for a variety of problems, let's say tuning hyperparameters. However, traditional optimization analysis usually tries to prove convergence bounds, okay, which are very nice because it tells us, for example, if there's an optima, okay, somewhere, let's say for strongly convex functions, convergence bounds tells you that after a k number of iterations, this distance between my iterate and my optimum should be bounded by some function r of k, where this goes to 0 as k goes to infinity. Okay. But there's another approach to try to understand the dynamics. Okay, instead of looking at a bound of how fast it converges to the optima, we can come up with some dynamical models that models this behavior of such systems. Okay, so for example, we can model this stochastic gradient descent by coming up with another nicer dynamical system, such that their difference becomes very small in some limit. Here, this eta is the learning rate. So in the limit of small learning rates, the dynamics of this two becomes very similar. Okay. Then the nice thing about this is you can then, for small learning rates, study this nicer system to try to understand this theta k, which is a more complex system. And this approach, of course, is not new. It dates back to the analysis of finite difference algorithms using modified equation. For example, the Lex-Friedrichs scheme for transport equations, where you can understand its fluctuations by this modified equations approach, right? Idealizing as a continuous time dynamics. So we can actually do the same thing for stochastic gradient descent. We take the stochastic gradient descent and we actually derive a stochastic differential equation that has a deterministic drift term and a noise term that depends on the gradient covariance of the stochastic gradient descent. And in this case, we can pass the study of dynamics for SG to this SDE, which is in some sense easier to analyze because we can apply continuous time tools to it. And this has yielded, first of all, we have to show that these two are actually rigorously related, and we show a weak approximation results of this SME to the SGD, okay, this differential equation. And we can also extend this result to higher order approximations and also different kind of SGD, like adaptive versions and momentum versions. Okay, so theoretical. So why do we want to do this is because once we have this system, then we can apply a variety of tools. For example, if you want to know how to tune the learning rate, then this becomes the stochastic control problem, where we have a lot of tools to study it. For example, the Hamilton-Jacobi-Bellman equations, and we can do that. So it turns out that we can actually analyze using this kind of approach, where you model the dynamics of a discrete algorithm by a continuous system to formulate tuning learning rates. And also, we can analyze different variants of the model and how it affects training, for example, batch normalization. And finally, in adversarial training, we can also apply this kind of methods to improve adversarial training. Okay. So I've talked a lot about the first, machine learning via dynamical systems, but I also want to spend some time to talk about the other aspects. And the second aspect is machine learning for dynamical systems. Okay, previously we really thought about doing machine learning in a static setting, right? So, but often supervised learning has to be performed in a dynamic setting, right? For example, we want to forecast the price, or we translate a sentence, a very long sentence, or we want to study the response of some mechanical system under some forcing. So what is the common trait to all of these problems is that each output doesn't depend on just one input, right? But it depends on the sequence of inputs. And you not only need to model one particular relationship, because your output could also be a time series, you need to model a sequence of such relationships. Okay? So this gives us a nice opportunity to investigate how, if you apply deep learning, let's say some sort of neural network, a deep neural net, to accomplish, or to tackle some of these tasks, you have a very interesting interaction between the structure, the dynamical structure that we talk about in the model itself, and also the structure in the data, right? The data, or the target that produces the data, also has a dynamical structure. So let me give you one example of this interaction that we have discovered in our research. So to make it more concrete, the static setting, we are really interested in modeling some function f star, right? But in a dynamic setting, we are looking at inputs and outputs not in the form of vectors, but in the form of a sequence of vectors, where the sequence can be discrete or continuous. And our target is, again, a sequence of functionals, right? Each of which depends presumably on the entire input sequence. So the goal of supervised learning in the static setting is to learn and approximate some function, f star, but the dynamic setting, we're trying to learn or approximate a sequence of functionals, h star, k, where k is the temporal sequence, the sequence index. And one example that accomplishes this is the celebrated recurrent neural network architecture. Okay, so this is a very classical architecture. So what it does is to introduce a hidden state, which we call h, that evolves in time. Okay, this time index is k. That at each time it takes into input, takes the actual input time series as a forcing term, and then the output or these predictions is actually read off this particular dynamical system. Okay, so pictorially, you can think of this as a hidden, introduced hidden state, and a sequence of inputs is being forced into the system, and the output is read off from this hidden system. And what's nice about this is that once you have specified these parameters, this dynamical system actually parameterizes a sequence of functions or functionals together. Okay, each of which depends on the entire history up to that point. Okay, for example, y3 is going to depend on x0, x1, x2, and so on and so forth. So then training this RNN is just adjusting these parameters, which are finite dimensional, right? So there's only finite number of them. But together, you can approximate a sequence of functions. So the key idea in RNN is that it actually approximates a sequence of functionals together via the introductions of hidden dynamics. So actually, for those who are familiar with the Morris-Wansink formalism, this is a little bit like the reverse of the Morris-Wansink formalism. Okay, in the Morris-Wansink formalism in statistical physics, you have some partially observed Markovian system, and you're trying to close it. That means that I only care about certain observables. And what I do, how I do it, is to introduce some memory kernel into the system so that we can close the system. Now, recurrent neural network is different. It's the exact opposite. You have some system that actually has memory you're trying to model. And what you do is to introduce a hidden dynamics so that it becomes partially observed, but this system becomes Markovian. And then you're able to approximate this memory. Okay, so this connection, I think, is quite interesting. And one particular problem with RNNs is that what we found empirically is that when you deal with sequences with long-term memory, let's say you have a very long sentence, you try to infer something from it, or very long time series that you try to predict that depends on signals far away, then empirically it is shown that this RNN do not perform well. But there's no concrete explanation as to why this is the case. So can we investigate this problem, using this the approach that we had before? So it turns out we can, and we're going to apply a lot of simplifications. For example, we're going to take the continuum dynamics kind of approximation again, and then we also assume some linearity so that this becomes a linear dynamics. So you can think of this as the simplest form of recurrent neural net, okay, which is just a forced linear dynamical system that has some input x, and the output is just read off from it. So if you observe this hypothesis space, actually it's a sequence of linear functionals. Each y hat, okay, so this should be a hat here. Each y hat depends on the entire sequence of inputs up to that time in a linear way, okay, because it's a linear dynamics. So then we can ask if we use this to approximate a sequence of target linear functionals. Okay, some functionals is given to you as follows. How well can we do? What type of linear functions can we actually learn efficiently? And when we say efficiently, we mean with a small number of neurons. And how does this relate to memory? Okay, so that's a interesting point. And what we can show using some approximation theory and also, as well as optimization analysis is that efficient approximation is possible if and only if the target functionals are smooth and have exponentially decaying memory. Okay, so what do I mean? Instead of defining them, I just want to show you the intuition. So here are two sets of functionals. Left-hand side is easy to approximate, and the right-hand side is difficult. So what are some properties of this? So you can see that the input time series is actually the same, right? But the output time series on the left, the input is very smooth in time, and the output is also smooth in time. So this means that this h star t, as t varies, should be rather smooth. Okay, so but on the right-hand side, this is not the case. Okay, when it's not smooth, then when this input is smooth, the output is very jagged. But this is not only phenomena. You can see that the input kind of stops changing after a while. Okay, and on the left-hand side, this output also stops changing. However, the same thing cannot be said on the right-hand side, where the output still changes drastically. So this means that the output here actually depends not just on the immediate vicinity of this input sequence, but maybe somewhere pretty far along. So the right-hand side is also a situation where you don't have, you have possibly some long memory. Okay, so armed from this intuition, we can actually define smoothness and memory in a precise way. For smoothness, we can think of it as just a regularity of this map between from t to the result of applying my functional to a constant signal, right? Like this. So E is a constant signal. And then the memory can also be just understood as temporal decay rate of the derivatives of this mapping. Okay, so that means that if I input stops changing, how fast does the output die down? Okay, if it dies down very quickly, then it's small memory. So once we have this precise definition of memory and smoothness, we can actually show that this approximation is possible. Efficient approximation is possible if and only if these two are satisfied. And what if it's not satisfied? For example, if you have some memory that doesn't decay exponentially, then what happens? We can show that this number of neurons required for approximation actually explodes exponentially. And we can think of this as a curse of memory in approximation, much like the curse of dimensionality that we face in function approximation in the spatial domain, but this time it's in the time domain. And what's more is that if you study the optimization dynamics, you can also see that the optimization also becomes exponentially hard when the memory increases. Okay, and in fact, there's also a separate facet of cursor memory optimization. Not only is it difficult to approximate such functionals, it's also very hard to train your network using gradient descent. So I think this is an interesting finding because this concerns the compatibility of the dynamical structure that's in the data, or in this case, H star, which produces data, and the model, which is the recurrent neural network that has in itself some decay properties. So I would say a few words about extension of this kind of approach is that we know in time series analysis in machine learning community, there's a lot of different models being proposed. For example, we have the recurrent neural network and all of its variants, but we also have convolutional based methods like WaveNet, introduced by Google. And there's also transformers, which are very, very popular methods used in particularly in natural language processing today. So one pressing question is that how are they really different? And when should we use which? Now, of course, we can have practical investigations of it, but it would be great if we could have a theoretical investigation of it. So the very simplified setting we had before of approximating linear functionals by recurrent neural network turns out to be a rather useful arena to answer this question. So we can actually use the exact same setup, but change the RNN functional hypothesis space, for example, to the WaveNet hypothesis space. And then we ask, what is the structure that's required in my target functional so that we can form efficient approximation? So in this case, we can show that whereas RNN performance depends on this memory decay property, the WaveNet CN doesn't depend on memory decay, but rather it depends on some special notion of regularity. You can think of it as a more general notion than sparsity. So as you can see from this input-output map, right? The convolutional neural network really, its field of vision explodes, exponentially through the layers. So it's not afraid of being dependent on parts really far away. But what is really, not capable to deal with is that you have very complicated dependence on, every single, macroscopic scale. So if you have very sparse signals, let's say this signal only depends on 1, 2, 3 signals, then you have very efficient approximation, and that's the intuition. And here we can actually make this precise. So the insight here is really when you talk about time series modeling, you really need some structural compatibility between the model, right? So RNN model has some, because it's a dynamical system in a differential equation, it has some decay structures, and WaveNet has some sparsity structures. Okay, or we can make this a bit more general, a general structure that allows it to perform better for certain applications. Okay, so I guess I have like a few minutes. I'll just briefly talk about machine learning of dynamical systems, and there will be a talk later about my collaborator on introducing some more work in this area. So machine learning of dynamical system is a very vast field. Okay, so I'm not gonna, not in a position to also give a complete, coverage of that. But I just want to say that there's some interesting angles you can think about this problem. So the basic setting of learning dynamics is following. So you have some high dimensional dynamical system, possibly high dimensional, and we can get some observation data of its trajectories, right? And then there are a few possible goals, right? For example, the first goal is system identification. So we're trying to learn this particular function f. And then we can also say, model reduction. For example, instead of learning this f directly, we can learn a reduction function that maps this high dimensional system to perhaps a lower dimensional manifold, Rm. And then we can construct a new dynamics on this Rm space, okay, such that this in the reduced coordinates, the dynamics is captured. Okay, so of course this phi is not arbitrary. This reduction function has to satisfy some properties, and there are different ways to impose a property. For example, if you want to do some prediction of weather, let's say which Rayleigh-Benard convection is a model of this convection phenomenon in weather. Lorentz model basically does this reduction where we can reduce it into, let's say, 3-dimensional system. And if you want to do weather prediction, of course, you want your reduction to be in some sense faithful, that you can reconstruct approximately at least the original dynamical system for, let's say, prediction of weather. So in this case, you really need your reduction to satisfy some reconstructability condition. And then there's some other kind of applications where instead of this reconstruction, what I'm interested is perhaps a very macroscopic property of my system. So for example, here, this is a very well-known problem where if you take a DAA strand or any long polymer in fluid, it's going to move, due to electrostatic interactions and also fluid mechanical interactions in the fluid. So it's going to move and it can unfold. So this strand is going to unfold, and it's a very important topic to study how the strands actually unfold. So here you can see that this is a very high dimensional system. Each of these molecules is going to have 3 coordinates, right? But what we're interested in perhaps is only the evolution of this length. So building a reduction model, you can think of it as a closure problem where if you're only interested in certain macroscopic properties, how do I do this reduction? And you want the reduction to actually preserve the dynamics or close the dynamics for that property. Okay, so there's different kinds of reduction problems one may be interested. Now, I think it's useful to think about 2 viewpoints in how do you learn dynamics, whether it's a reduced dynamics or original dynamics. The first one is more from a machine learning approach, right? We start from some data, and our goal is to regress this function f, which specifies the dynamics, okay, using some generic hypothesis space. Let's say, linear combinations of polynomials or some combination, let's say neural networks. And then we say that we really need to build some physics into the problem, right? So what we can do is to use different loss functions or hard constraints or soft constraints to deal with this problem, to add some constraints into my generic hypothesis space. Now, there's another approach you can think of it as a modeling approach, which is we start with some physical model, okay, and we maybe gradually make it more and more complex, and we build this hypothesis through this model, physical principles, and then we fit some unknown parameters or functions from data that's involved in building this hypothesis space. Now, this is no essential difference between the two because one is sort of ground up and one is from top down. But I think it's interesting to think about, which approach could be, more suited for what kind of problems. The first statistical approach is very popular, containing sparse regression, symmetry, preserving neural networks is being talked about yesterday. And the modeling approach is kind of familiar because a lot of this traditional physics and chemistry models actually go from this, except that we figure out everything with our head and doing numerical measurements. Okay, so can we actually, my investigation here is that can we actually use this modeling approach and combine it with learning to achieve some goals, perhaps a little bit better performance than the statistical one. Okay, so there's 2 works we use this approach. I'm only going to talk about one of them in 1 minute. So here, our goal is to really model some dissipative dynamics. Okay, so general dissipative dynamics. And the approach is like this. We first look at what is the most general and useful phenomenological principle for this dissipative dynamics. It turns out Onsager has celebrated paper on linear response has a good model for it. Okay, so it goes something like this, where you have a differential equation that is almost like a gradient flow, except with the dissipation matrix M, that models this dynamics. And this you can model this, a wide variety of dynamics in a setting of near equilibrium. And then our approach is basically take this Onsager principle and generalize it by introducing more complicated terms here that models some more complex aspects of this dynamics. For example, when it's possibly away from equilibrium, far away from equilibrium. And then each of these functions has to be fitted from data. So what we can do is to leverage this good approximation properties of neural nets to learn each of these functions from data. Okay, so this is kind of from a modeling approach. Some advantages is it captures general dissipative dynamics accurately because we have built that assumption of dissipative dynamics from the very start. Okay, and not as some sort of constraint, hard constraint that's put into a generic neural net. And it is very stable, and you learn some physically relevant quantities. Okay, so that's one example of how we can do this. And in this conference, we have a paper that does this from another point of view of quasi-potentials and stochastic gradient flows. So I will not talk about this today since there will be a session later. Okay, so sorry, I have overrun. Maybe I'll just take 1 minute to talk about some my thoughts on the outlook. Okay, so first of all, the topics I discussed before, is of course only a small fraction of the very large amount of work that's being done in this area with a lot of researchers. So I'm not attempt to say that what are the gaps that needs to be filled, because the gaps are everywhere. But I will talk about some high-level general questions that I thought is interesting to me. The first question is, why composition and dynamics in machine learning? So we have some results to show that we can do things with composition and dynamics, okay, under very fairly weak conditions. But we don't really have a good satisfactory answer about what kind of relationships are best suited to be to apply composition or dynamical, hypothesis space, let's say a deep residual network, to approximate. So in other words, what are some nice, what is the equivalent notion of regularity when it comes to approximation, not by linear combinations of basis functions, but by composition of these functions? And there are partial results, due to very interesting papers, written by colleagues and other researchers. But we don't have a good picture of that yet. And I think that's a very important question to be able to understand this machine learning and its dynamics. The second one is a how question. So it's like, how do we simplify? Okay, so this is simplify the ML plus science workflow. So now, once we start to apply these machine learning methods to scientific disciplines, we have a lot of different kind of models, each accustomed to a particular scientific application. So the goal, of course, is try to streamline the methods and really talk about what are the essential differences between these methods and when should we apply which method. So hopefully we have a streamlined description of how we do this. And of course, this is not a goal specific to scientific applications, but I think in scientific applications, we have a more unique way of trying to tackle this problem because very often in the applications, we have some notion of the structure of the data, right? So the data generation process is usually some physical chemical process that we have some description over. So there is a hope, for example, we can actually connect the structures that is present in the data and the structure that is present in the model. And finally, what's very interesting is what new machine learning problems actually arises in this dynamical setting, especially in the scientific applications. So I think this is very important. How can we sort of contribute back to the machine learning advancements? And here, one particular example, for example, is that the big difference between machine learning applications in sciences and the traditional ones is that the data generation process is not really fixed. In image recognition, we take the pictures first without thinking about what happens after that with the machine learning researchers, right? So the natural image, natural language are produced independently, very often independently of machine learning. But in scientific applications, almost all of the advancements now, the machine learning researcher is also involved in the data generation process. So there's a very important press for active learning investigations, so something that connects how we generate data and for which particular problem. And it is especially prevalent in the dynamical setting because it's impossible to naively sample trajectories without understanding where those trajectories are supposed to go in your learning algorithm. So I think this presents a very interesting series of questions back to machine learning and how this data generation and sampling process actually interacts with the machine learning model. Okay, so with that said, I have come to the end of my talk. Sorry for overrunning, and I'll be happy to take any questions maybe later in the break.
Okay, thank you very much, Qianxiao. I think it's very, very nice, covering a lot of very interesting, I think, deep questions. So are there any, there's a few questions on the chat. Perhaps we have time for a couple of quick of them and then defer the rest offline on the Slack or, so perhaps, I don't know if Nick, just in reverse order, do you want to unmute yourself and ask to Qianxiao your question about stability?
Sure, yeah, very nice talk, super interesting. So I was interested in this result about, if you're trying to learn a dynamical system using an RNN, then that dynamical system needs to have this kind of exponential forgetting of past inputs property. That basically memory will really hurt you. So I was wondering if this is basically coming from the fact that the RNN is assumed to be linear, right? Because if you have a linear dynamical system, then unless all eigenvalues have magnitude 1, it's either going to be exponentially stable or exponentially unstable. And clearly, if the dynamical system is exponentially unstable, then it's not going to be very useful for learning. So I would imagine that your RNNs are kind of restricted to be stable, in which case it kind of seems very natural that, the target function is going to need to have this kind of exponentially decaying memory property because it's built into the model that that property is there. So I was wondering if you could comment on a couple of things. One, in general, does this suggest something that like being closer to the edge of stability would actually be helpful for learning dynamics? And second, if the RNN were nonlinear, which I understand is a much more difficult problem to analyze, would you expect that maybe this condition would be relaxed because you can have more fine-grained notions of stability? You could have some kind of Lyapunov stability that's not exponential, for example.
Right. Okay. Thanks for the very interesting question. So first of all, yeah, I agree that as I said before in the next slide as well, the main insight we gain from this analysis is that you need some compatibility between your data, your target property and the property of your dynamics. Okay, whether it's a recurrent neural network dynamics or is it a convolutional net, right? So here, of course, the linear system. You're right in saying that the linear system, if you want to be well behaved, it has to be exponentially stable, and then you have this decaying eigenvalues, and that gives it a constraint, right? To have that structure. So it is very natural. Yeah, I agree that after doing the analysis, this should be something very natural, and it goes beyond recurrent neural network. In the convolutional net, the structure will be a bit less direct, but the idea is still that you need some compatibility. Now, going from linear to nonlinear system is a very interesting question. So what we did is in our investigations, we try to see whether the same actually holds for nonlinear systems first numerically. Okay, and a lot of this analysis does hold numerically in the sense that when you incorporate some long memory structures, which we can make precise in this case, what kind of systems H stars are like long memory. And the behavior predicted by the linear system is not far away from the predicted behavior of the nonlinear system, especially when it comes to optimization. So there's two separate problems here. One is whether you can approximate this function efficiently. Now, this problem is hard to check numerically because you have to show the existence of a good approximation, you need to actually construct it, right, numerically. But we can at least show that to learn this kind of long-term relationship in nonlinear setting is also difficult. Okay, but of course I agree that there could be nuances that for nonlinear systems, perhaps a more general notion of stability should be considered when it comes to defining what functions are more easily approximated, whether it's approximation or optimization. Did I cover all of your questions or did I miss another one?
Yeah, I think so. Cool. Thanks a lot.
Okay, thank you.
Great. Yeah, so I think that there's a lot of questions in the chat that I would suggest that we put into the Slack channel, and maybe there's time offline during the break to argue. There's maybe just one that I think we already exchanged a little bit with Lenka, and I would love to hear your thoughts about it here
Sure.
In real time. That really concerns this connection between the continuous time and the discrete time, which is, I guess, a very core and fundamental aspect in dynamical systems. And the tradition is that you typically view the discrete time as a necessary evil, right? You need to discretize things to run them in the computer, but in a sense, you prefer the beauty of things in continuous time. And somehow in machine learning, there has been some debate recently about whether this paradigm is also true when it comes to the properties of the gradient, like optimization algorithms, right? Some people have, defended that, like the learning rate being non-zero and non-negligibly small, hold some hidden generalization properties, this kind of like an inductive bias, and I know this is really not something that is settled, and I would be very curious to hear your thoughts about this topic, like the benefit,
so,
whether you believe that there's an implicit bias of discrete time in learning.
Yeah, so from the outset, so the most direct question one can pose is basically for optimization. Very often we're interested in asymptotic properties of dynamics, right? So we want to optimize it for a pretty long time till convergence, and we talk about convergence property, long time properties. In this case, there's actually very little control, at least from a theoretical point of view, you have between the similarity of a continuous time system and its discretization, right? So we can show that every finite time, if you let the learning rate go to zero, this continuous system is always going to be a good model for the discrete system. However, when we talk about generalization error, you're really training for very long times, okay? And in this case, you are fixing the learning rate and let time go to infinity. Now this is a different kind of problem, right? So the asymptotics will be different, and in that case, it is true in general that the discrete dynamics may have different asymptotic, let's say, distributions from the continuous one. Okay, so it is true that it may be the case that some properties could be reviewed that only holds for the discrete case, but not the continuous case. Okay, for certain, let's say, numerical algorithm or a certain loss function. Okay, so one cannot rule out that possibility. However, I think it's also, we hope, like, it's the same thing, right? So we have a numerical, for example, numerical analysis. We could come up with a finite difference scheme that when you make the grid finer and finer, you actually approximate a different kind of system that has very nice properties, but is something that you cannot describe. Now, that, of course, that happens. That could happen, but one can also argue that it should not be the goal of designing an algorithm that you can try to understand and generalize. So we hope that we'll be able to come up with, we want to be able to come up with the algorithms or regularization schemes for which they behave nicely under discretization, right? So for example, you have a dynamical system that has that verifies property A, B, and C, then we can ensure that the long-time behavior of this dynamical system and its discrete dynamics is similar. And that could be a good goal in how we design the algorithms. So the algorithms that we are seeing now, let's say just applying stochastic gradient descent to random samples, may not have that property, but it also doesn't mean that good algorithm has to not have that property. So I think I agree with that. There's no theoretical guarantee, as far as I can see, in general, that they must agree. But I think it is advantageous that we come up with algorithms for which we can ensure that they agree.
Great. Lenka, do you want to add something?
Yes, I actually do want to follow up on that, but I also think we should let at least 5 minutes before the next session. So I really hope to thank you, Qianxiao. I should learn to pronounce your name. Sorry for that. I really hope you join us on Slack and that we can continue this discussion in the designated channel to your plenary talk.
Sure, I'll be happy to.
We look forward to see you there. Thank you, everybody.
Thank you very much, everyone. Thank you again, Qianxiao. Thank you. Great talk.